Okay. So Gauss's law tells us that the charge for the flux, I sub u, through a closed surface is 4 pi k cubed, where Q is the charge of flux. Spherical regions for A is less than R less than B. Uniform charge density. Rho. But we want to find the electric field if R is less than A, R is greater than B, or R is between A and B. Well, that kind of looks like this. Okay, I'm just going to draw a circle. Okay, so we've got a circle of radius G, or sphere of radius G, that's a little sphere of radius, and a sphere of radius A. So R can be less than A. If R is less than A, we want to look by our sphere. Centered at the charge, centered at the center of the spheres. Where the radius of this thing is less than A, okay? Now, our charge is, let's indicate charge inside here. Under the dots. But there's a whole bunch of it, and it's just really a continuous distribution with density rho. Okay. The question is, what's the electric field at the surface here? There's your sphere. Centered at the same, at the common center of these other two spheres. Flux through the closed surface, this is closed surface, is 4 pi k cubed, where Q is the charge of flux. So what can you tell me, or what would you want to tell me about the electric field? Okay, we have to digress quite a bit to what we did last time. People couldn't tell me what the flux was, what flux was. We had to go through the whole thing. The surface influence, electric fields and normal vectors and all that stuff. And we came back to this, and you really need to digest that and understand that deeply. Okay, so make sure you do. It's only been 2 days since last time. Make sure that by the time the homework is due, and by the time you go through the homework, you put that down. So I've got this surface in here, center to center, and I want to know what the flux is. Actually, I want to know what the field is. Because of the symmetry, the field has to be uniform with this thing. If I rotate the whole system or rotate this surface itself, it can't make a difference in the field because of the symmetry. It follows that and the fact that there's no charge enclosed within this surface, that there's zero electric field on the surface. And since we can put the surface like this through any point inside the inner shell, inside the radius A, we know then that the electric field throughout the inner shell has to be zero. So if we want to go now to the second easiest question is, what's the field out here? And to find that out, we put a surface will be a sphere, radius equal to the distance from the center to whatever point this is. Okay. And now we apply Gauss's law. Well, what's the first thing we want to do to apply Gauss's law once we have this surface created? Okay, we're trying to find the electric field at a point out here. So we construct a sphere which is symmetric with respect to the distribution, meaning it's got the same center as these two spheres. Okay. So that if I rotate the whole thing, nothing changes. Okay. So if I rotate the whole thing, but I keep the point here, I'm going to get the same answer as if I leap it 1 inch. The application of this is that the field has to be radial, because only a radial field is going to be symmetric with respect to rotations of that sphere. So on this sphere, radial field can't change its magnitude one point of the sphere to the other, because that would make everything, that would ruin our symmetry. Okay. So if one of these vectors isn't radial, if it's off like this, then if I rotate it, that off vector is going to be over here. So they'd all have to be off like that. Okay. But that's not no symmetry. Same orbit. Okay, so electric field radial by symmetry. Now I'm going to say on the surface, E is radial and uniform, and that's by symmetry. Okay, so what's the expression for the total flux? It's due to the charge Now, we worked this out, we talked about it, people got it in their heads, that was good. Okay. Uniform distribution rho, if we multiply rho by the volume that the distribution occupies, we get the total charge. That's what charge density means. The volume occupied by the charge is volume between these two spheres. Well, the volume of the outer sphere is 4/3 pi b cubed, right? Whereas the inner sphere is 4/3 pi a cubed. Region between is the difference, which is 4/3 pi b cubed minus 4/3 pi a cubed, which is 4/3 pi times b cubed minus a cubed. We multiply that by rho. Now we have the total charge enclosed if R is greater than B. That's the total flux in the Gaussian surface. In every case, our Gaussian surface is a sphere. Center of our distribution. This only works because the distribution is spherically symmetric. So if R is greater than B, there's our total charge. Well, our flux is due to the total charge. And we write it down. It's starting to look kind of long. You got a couple of fours here, a couple of pi's here. You can, next time you write it, you can use a pi squared and 16. Okay, but there's your flux. Now, that doesn't help all that much until we have another expression for the total flux. The other expression for the total flux is just the field E times surface area. Shows the total flux is just the sum of all of E's times the surface areas. If E is uniform and always perpendicular to your area, then it's just E times your area. It's just E if it's uniform, if the magnitude of B is always the same, then it's always normal, then it's just E times your area. You can factor out that common E, and sum of your areas is total surface area of your, so total area of the surface. Okay, so tell me, field is always normal to surface here. So E dot dA is just EDA. And that's just E times surface area. Now, sum of all your EDAs is phi sub B. So phi sub B is just the field times your surface. Well, given that, tell me what the field is. There you go. Here's Gaussian surface. The sphere radius are about the center of the distribution. By the symmetry, the electric field has to be radial. If R is greater than B, then you've got all the charge inside here enclosed within the surface. So you have flux 4 pi k cubed. And we figured out what Q was. There's your charge. Just rho times the difference of the volumes of the two spheres. Then the field, always being normal to the surface of the sphere, means E dot dA is just E dA, no vectors. Just the magnitude of D times the magnitude of the area. So when you sum up all your area increments, you just get the total area of the surface, and you can factor out E from this summation. So phi E is this, and it follows then that I'll use S for the surface area. We're going to divide this by the surface area, which is 4 pi r squared. Get rid of this 4 pi. You're going to end up with this. And this is just the charge enclosure. But everything here except the K is the charge enclosure, which we figured out here and at local. Now, all this is just a charge enclosed with your R squared. So it's in the case of a spherical charge distribution, a spherically symmetric charge distribution. Field at any point depends only on the charge closer to the center. So now we get the one that I have to think in shape to do. What's the field at distance R if A is less than R less than B? Okay, well, if R is between A and B, then the surface is going to be in between here. And really all you have to draw is what's inside the surface. You don't care what's outside. So you're going to draw a surface like this. Here's your radius R. And inside that is your circle of radius A. I'm gonna draw it smaller than I did over there because the radius would matter. And it would have my circle go through my arm. Okay. So you have this, and now you got the charge. Gaussian surface. Here, charge inside the surface is just 4/3 pi rho times r cubed minus h. Instead of b cubed minus a cubed, which means charge in the whole shell. We only have part of the shell, and it just goes from A to R. Okay. And the rest is pretty straightforward. So just some dots, we're going to get E equals this. The same expression before, except instead of B, we're going to have R. And of course, R is going to be less than it is here. So you might have a stronger B. Okay. I think it does, because that's pretty much, you had most of that, and you're about to write out the rest, I think. Okay, so a little curveball at you. Got a section length L slit. Okay, so we've got an inner cylinder of radius A. And an outer cylinder of radius B. We've got some ionized gas or something in between. So we've got a uniform charge distribution. We're going to assume it's uniform at first. And then we're going to ask what happens if it's not uniform. Okay. So how do we get the field? So we want Gaussian surface for which field's always perpendicular. So that we just multiply the field by the surface area increment, because the field is perpendicular, then it's normal, it's parallel to the normal vector, right? So the field's always perpendicular. And I could say always uniform, but it should be very specific. Always of the same magnitude. So what kind of surface would that be? And I'll also mention these are coaxial cylinders.